Okay, so today's presentation will be from Helen and from Hans, hopefully. And I will have some several minutes to talk about our final report. Okay, so I think we can start from the first presentation. So maybe I will stop this presentation first. So yeah, maybe Helen, are you ready?
Okay.
Yeah,
Yeah, I'm ready.
yeah. You can share your screen.
Can you see my screen? Can you guys see my screen?
Yeah, yeah, we can see. Yeah.
Okay. Can you hear me well as well?
Yes, yes.
Okay. Okay, so hi everyone. My name is Helen Sarvi, and my topic for the PBL class is going to be vectors in two dimensions. So first we need to understand what are vectors. And vectors are quantities with magnitude and assigned direction, and which gets them as shown with an arrow to specify the direction. And what this means is just that A is the initial point and B is the terminal point of the vector AB. And I also must clarify that a vector quantity has a direction and a magnitude, while a scalar has only a magnitude and no direction. So scalars are just numbers. And by placing a vector in a coordinate plane, we can describe it analytically by using components. So we can represent a vector v as a1, a2, where a1 is the horizontal component of v, or the x, and a2 is the vertical component of v, or the y. And the vector v can also be expressed in terms of I and j. So it can be something like a vector v is equal to a1I plus a2j. Now let's talk about some operations with vectors. And we have this formula here where we subtract the p components from the q components to find the component form of a vector. And components are basically scalars, and they allow us to break a single vector quantity into two or more scalar quantities. Vector components are used in algebra to add, subtract, and multiply vectors. And we also have magnitude, or a length of a vector. And we put these two bars, the two parallel bars in B. So we want to clarify that we are talking about magnitude. And magnitude, we say that two vectors are equal if they have equal magnitude and the same direction. So in other words, two vectors are equal if and only if their corresponding components are equal. So applying the Pythagorean theorem, we obtain the formula for the magnitude of a vector. And in the right side, we have 2 points. So in this case, we first find the components, and then we multiply the square, and then we sum them up, and then we find the square root. And here let you guys I want to show you guys some properties. And I didn't do any exercise here because I thought it was too boring for you, and also it will take a lot of time. So I just left some properties here. And in this case, the multiplication by a scalar, the scalar is just a number, as I mentioned before, so it can be any number. And also, I want to talk about applications of vectors. So, vectors have many real life applications, and many of them in physics, including situations involving force or velocity. For example, let's consider the forces acting on a board when it's crossing a river. So the boat's motor generates a force in one direction, And as we know, the current of the wind generates a force in another direction, and we cannot control the wind. So both forces are vectors, and we must take both the magnitude and direction of each forces into account if we want to know where the boat will end up going. And here in another half, where when we want to go to a place, this is like a super normal thing, and I already talked about this in my video. But when we're going to somewhere, we need to know two things: how far is the place we want to know, and in which direction. We not only need to need we not only need to know the distance, but also the displacement. Because let's say we want to go to our house, and our house is 2 kilometers on the right from here. So it's not the same going 2 kilometers on the left from here, because even if we're going 2 kilometers, where the place we want to know is in another direction, so we're not end up going to the place we want to go. And another basic application could be how we judge the direction of falling rain droplets, and when we're moving on a rainy place. Based on how fast we move, we can guess the direction of the falling droplets by something that is called the triangle law of vector addition. And this triangle is just that the third side of a triangle represents the vector sum of two vectors. But there's a thing: the term point of the first vector must match the initial point of the second vector. And also about projectiles, because throwing a ball to a maximum distance needs a specific angle. They say that is 45, but I'm not sure. And there is almost nothing about there's almost nothing in physics that can be done without vectors. They are super important tools when it comes to improving perceptions in geometrically tricky situations, and vectors are everywhere, wherever there's a force or a field, and they present us with a relatively simple way of making sense of complex ideas. Thank you. Hi.
Yeah. Any questions for Helen? You can write in the chat box. Okay, so the factors is actually uh, one field that really includes most of engineering fields, like maybe also in the most on physics. Uh, if you want to write or formulate the force, every force in the world, in our real world, we can rewrite them in form of vectors, right? And also, if you study calculus, in calculus 2 you will also learn vectors, and you will learn also vector calculus. So every calculus aspect you need to transform and do it in a vector. So if you feel that it's already okay for you and not really that much to say, or maybe you want to have some discussion, please you can chat in your chat box. You can write your question. Anything you can write. It doesn't need to be a question. You can also write your thought, your maybe your feeling about vectors or anything that you want to discuss. Okay, so anyone? Ardian, what it means by a vector can be placed in a, you mean new position? You mean new, right? The NWE. Oh, okay. It means that you can move your vectors. Okay. I think I can help you with that. Wait a minute. Okay, wait a minute. Okay. Okay, you can see my screen. Okay, a factor can be placed in a new position without rotating it. So what it means is, if this is a factor, okay, so we have a factor like this. Let's say this is factor A. Okay, uh, if you move out this A, as long as it has the same magnitude and the same direction, it's still a factor A. Okay, so if we move out this like everywhere, we can still do that. Right? And if we want to, um, let's say we have this factor A, and also we have uh, a vector here that is maybe factor B. What can we do is we can also make another vector that is maybe around here. We can also call this is vector B, and we can see that the resulting vector is this vector A plus B. Okay. Okay. I hope you understand what does it mean. Okay. So if you take B going to go here, okay, this will become negative B because it has the opposite directions of the factor B. Okay. And this resulting A negative B. Okay, I hope it's still uh, has similarity with factors in physics because it's basically the same problem and the same fields. Okay, for also for physics. Okay, but in calculus we are more more basic. Not in usually in physics, you can use vectors for force, magnetic fields, and so on, right? But in calculus, we are really use it in a raw way, or in a raw form. That is, a vector is something that has value and also directions. Can be anything, and usually we are more elaborated in how we perform the calculations and how we perform some of the formula in the vectors. What Helen just presented is the vectors mostly in the two dimension. Okay, but we can also elaborate vectors in, so it's in 2D and also three dimension. Okay, if two dimensions, it's a line, right? It's making a line like that. But in three dimension, aside from the line, we can also look at, we will also have a plane. Okay, we will have a vector plane, and I think you better to read some of that. But the basic concept is still the same. It's still the same. Okay. Okay. Any other question? I will wait for a few minutes. If there is no question, we can move to Hans. Okay, is there any question? No? Okay, I think we can move to Hans, and thank you, Arden, for the question. Okay, Hans, are you ready?
Yes, bro.
Okay, please.
Can you see the screen?
Yes. Yes.
So I first want to go over the definition of inductional thinking again.
Can you speak louder? I think you need to speak a little bit louder.
Is this is this louder?
Yeah, that's good.
I want to go over the definition of inductional thinking again, real quick. So induction is a method of logic where one draws a general conclusion from a set of specific observations or information. And a simple example of this would be like observing swans in the park you go to all day. And as all of the ones you've seen are white, you conclude that the swan you'll see tomorrow will be also white. And even though that's a calculated prediction and it makes sense, it doesn't arrive at certainty, just like what I said in my previous video. However, this is not mathematical induction, and I will get to that in a second. So, how all of that connects to mathematical induction is that mathematical induction is also a logical method. So it's a method used by mathematicians to often prove theorems to see if it actually works for every natural number. So it works by using three steps, or formally known as PMI, or principles of mathematical induction. The first thing is that uh, we recognize the function at hand, or the theorem, and we first prove that the base case actually works or is true. And it's done by plugging in the smallest possible integer to the equation. And the next step would be what's called an induction hypothesis. That process assumes that if it works for n, then it should work for k plus 1, where k would be an arbitrary integer. And to prove that, we just plug in n equals k plus 1, where k would be just a, or the input for the base case. And if all of that works, then we can conclude by the principles of mathematical induction that P of n is true for any integer. Okay, here's the thing. that I wanted to talk about. Although mathematical induction seems like it employs the tactic of analyzing specific observations, which would be proving the base case and the next integer, and drawing a general conclusion that the whole function works for the next infinite set of number of integers, it's not actually the same as induction in philosophy. So this is the part where I missed in my video, and it's actually pretty important as well. So mathematical induction is actually a rigorous form of deduction. Um, uh, it's not really induction as in inductive thinking. Rather, it's just somewhat similar to it. So almost everything in math is deductive, and I guess the closest thing to induction in inductive thinking is mathematical induction. So I guess people just called it mathematical induction. Um, Prof, can you add something to this? I'm not sure.
Yeah,
Guess this
yeah.
is really confused.
Later.
Okay, okay. So it's considered a form of deduction because in order for the process to work, specifically the induction step or hypothesis, you need to have a deductive proof in the form of one case that implies that it works for the next case. So now let's get to an example. Um, First, we consider a statement P of n here. It's the formula here, and let n be natural numbers. And then we verify that P of n apply for the base case, and then we do the induction hypothesis, which is assuming that P of n is true for n equals k, then that would mean P of k plus 1 is also true. And then we just prove that P of k plus 1 is also true. So this function here basically says that the sum of consecutive numbers from 1 to n is given by the formula on the right. So now we want to prove that this really applies for n equals 1. So now let's just prove for the base case. We plug in the smallest possible integer, which is 1, and then we see that we get just 1, which is also the same if you cross-check with this. You also get 1. And then um, next we do the induction hypothesis, and then that just means that we plug in the next integer and see if it also works. So here k plus 1, k would be 1, so that would be 1 plus 1, and then you can see that the answer is 3, and if you also do it manually, which is just 2 plus 1, that would be the same. So at this point, we have proven that via mathematical induction that the function works for any positive integer or any integer. So here are some uses of mathematical induction, mostly in math. So you have the Fibonacci sequence, which is expressed by this formula here. Um, uh, it basically says that the nth Fibonacci number is the sum of two numbers preceding it. So n would be the sum of n minus 1 and n minus 2. And you also have the Eulers Identity, which was also proved by mathematical induction. And uh, this one is a pretty famous one, I think, the Tower of Hanoi, which here you have the equation that counts how many moves it takes for a n number of rings. But mostly it's used to prove properties of binomial coefficients. And you also may ask if there are any significance of mathematical induction in, say, real life or engineering. I start by saying that in real life, I think induction itself is basically everywhere because it's a method of logic. So subconsciously, I think you do this type of logic, like with the swan example I said at the front of my presentation. And in engineering, you I see you find algorithms that try to deal with usually with recursive things. So you see mathematical induction in computer programs in engineering, and I guess um, a lot of the calculations that people do in engineering um, and the equations and stuff was basically verified through mathematical induction. So maybe it's not directly applied to engineering, more of it's like one of the things that lay the foundation of engineering, as in math. So that's all for my presentation, and thank you. Are there any questions?
Okay, thank you, Hans. So, okay, maybe for questions first. Okay. Oh yeah, Blessing, you can write the question.
Do I just stop sharing here, bro?
Yeah, you can stop the presentation. Yeah, that is the question. Can you answer, Hans?
The I'm not. To be honest, I'm not sure. Maybe it's just used as a property when you're doing math. I guess I'm not sure. I honestly don't really know any practical applications other than like using it for math. I assume. Yeah, that's all I can say.
Okay. Um. Yeah, actually, the Euler's identity is generally used for to include the imaginary exponent, and then we can redraw the equation in a geometric interpretations as a circle. So that is the idea, and I think because it is related to imaginary component, and some of the, if you remember, um, the electromagnetism, I think it's also having um, some of the formula in physics, like in magnetic fields, uh, like an electromagnetism, it has some sort of imaginary number. So I think in some relations, the Euler identity, it can be also tied with the Maxwell equations. Okay, so yeah, I think that is the most obvious case for the usage of the Euler's identity. Okay. Yeah, most of the mathematical nodes, formula, proof, usually the real world application is mostly in physics, and because physics is talking about a fundamental science, not only about the engineering. So it's usually proven by some mathematical sort of formula, and one of them is the Euler's identity, and it is considered as the most beautiful formula in mathematics, the Euler's identity. But actually, I haven't talked about it yet, even in a calculus, because I think it is a later introductions for um, I think if you take the electrical engineering or electronic, or if you want to elaborate more in those fields, you will eventually get the Euler's identity. I think if you want to ask more, you can ask your, I think your calculus teaching assistant, Wolfgang. I think because his major is mostly about electrical or electronics. So I think he learns more about this Maxwell equations. Okay, okay, that's the Euler's identity. Any other questions? Okay, I think mathematical induction is one of the fundamental. Okay, let me share my notes. Okay, so uh, actually, if you want to talk about the mathematical inductions, okay, um, it is one of the uh, principles in problem solving in mathematics, in calculus, yeah, basically in mathematics. Okay, so we call let me write it as principles, okay, of problem solving, and I think these principles also can be applied in real world situations. Okay, sometimes because basically, if you learn math, you need also to learn about real world problem and how to solve them. So you need to take some principle in math and use it in the real world. And sometimes people cannot relate that, so they eventually just think that mathematics is only about formula, calculations, and how to solve the problem in exam. But actually, it's not that simple. If we think about the problem solving, first we need to think about our plan, right? First, we need to think about our plan. What you need to conduct, okay, or what you need to do first. Okay, let me write. So you can start with identify, right? Identifications, or if I write in that sentence, maybe recognize something familiar. So whenever you have a question in exam or anything that comes up in your real life situations, first you need to think of plan. Okay, don't rush to solve something. uh, do you recognize those things as something happened before, previously happened, something familiar, right? So first it's identifications, and second, recognize pattern. If you see any pattern and maybe you can draw a conclusion from that pattern, and then maybe you feel that you have or you can relate to other things, then maybe um, you can see something that uh, there's a line in between that maybe other people cannot see but you can see. Okay, so probably you can recognize pattern. And to solve problem, you can also use analogy. An analogy can be everything that you can think of and relate to the problem itself. And also analogy is helpful if you teach someone or you teach your junior, and then or maybe teach younger people that probably didn't really have much background of maybe science or engineering, and you need to use some analogy um, to help the person understand what the problem is. Okay, and then maybe you can also add something. Okay, introduce something extra. It can be anything as long as it is related to the problem and it can help to solve. Okay, if you just add something without knowing what will happen, it will be wasting your process, right? Wasting your time, right? And then take case by case. What does it mean? Sometimes the problem consists of several cases. The goal maybe it's just only one goal, but to reach that goal, we need uh, to work out from one case to another case, and then you can take several cases. Like for example, if you do the because in calculus you learn the integral, right? You learn the integral blah 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 dx. Maybe you see this integral as several problems, like you have the function itself or the algebraic equations, the algebra. The integral itself is just this one, right? This is the integral. So you can probably rewrite the algebra first and maybe change to another form, or maybe you need to rewrite in some other functions as well. So that is take case by case means, okay? And then sometimes you need to work backwards. So if you have already solved, sometimes we need to, maybe if you need to prove that it's correct, then you need to try to check whether your result is correct, and you can work backward or doing a reverse process and see whether it is correct, or to confirm whether it's true or not, right? And then next part is establish sub goals. So of course, this is what I mean in take case by case. Whenever we do that, this is our goal, and maybe to reach out this goal, we need to have several steps. Okay, sub goal 1, sub goal 2, and 3, and then reach the final goal. And all these things, eventually, sometimes you already doing it without really knowing what it means, but actually this is um, something that obvious in problem solving. Okay, and also probably this is the additional indirect reasoning. So um, we can use the proof by contradiction. We can also do that. And also the last thing is that we already discussed in this presentation. This is so-called the mathematical induction. So this following ideas is actually how we can think of our plan. Okay, think about a plan. So mathematical induction is already one of main idea or main plan on how to solve a problem. Usually, these inductions can helpful if you have proving statements that involve a positive integer. Like I think Hans already talking about that. Like if S1 is true, as a statement. Okay, statement about positive integer. If S1 is true, then S or N or K plus 1 is true whenever Sk is true. Then we draw a conclusion that Sn is true for all positive integers. N. So within this plan, okay, we can probably, after we identify, recognize the pattern, or maybe we think about analogy that we are using, or we think also introducing something extra, or maybe if you skip that, that's still okay. Yes. So within this all statement here, identification, recognize pattern, analogy, introducing something extra, taking case by case, work backward, establish sub goals, indirect reasoning, mathematical induction. Maybe not all will be applied to solving a problem, but at least half of this we have done um, in solving our problems, especially on your case, maybe in a calculus. So uh, it's important to explain your steps. Okay, like maybe if you have any problem, you need to explain to yourself like what you need to do first. Okay, so plan what to do, right, and how, and ultimately what is the conclusions. It's better if you know there's something red here or right, if you know why. This is practically necessary if you want to have uh, more value. Okay, if you just know what and how, you will get the results, but it seems that it's not helping you as a person. But if you know why, like if you can ask yourself like why you need to study, why you need to study at Taiwan, in Taiwan Tech. If you can answer this why, it can help you to establish your goal. And it's not just a generic expression for students who usually why you study so I can work. It's not helping. It's not helping. So for example, study, why need, so need study for find a job. This is just an example. Let's say it's find a job. Okay, find a job. Okay, let's say that's the reason you want a degree, right? A bachelor degree. Find a job, and then we can see some set of requirements of that job. First, what? Maybe degree, maybe experience, maybe some set of skills, either hard skills, soft skills, and yeah, maybe more. And you tend to approach this set of requirements during your study, right? At least this is what you are going to do. But every person, I believe, you need to have different approach, and because everyone is unique and everyone is having their own goal. So I hope everyone can pave a way or set of they can set plan something that is practically different, okay, from other students. Okay? So I hope you can plan out your idea, okay, and I believe actually mathematics, calculus is one reason that if you are really good at it, it doesn't mean that uh, how to say you have score, right? You have score like maybe we have like a minimum passing grade, like in mathematics and then also in calculus. But the score is just a score. It's just numbers in your transcript. It's just a letter in your transcript. Whether you get A, you get B, you get C. If you cannot apply, if you cannot apply in the real world situations, like for example, finding a job or maybe doing something in your life, if you cannot apply this, then all the knowledge seems not really helping. All right. So what I suggest is, and what I feel about mathematics. Okay. So whenever someone has uh, really good logic, like good logic, good reasoning, and he can calculate profit and loss for himself, I think he will be, uh, for me, this is what it gets. So mathematics is not just about solving an exam, but actually helping you in a real world situation and hopefully getting you to be a more logic person so that when you need to solve problem, then you can design a plan uh, and hopefully well devised plan, okay, to to solve your own problem. Okay. So that is actually math for me. Okay, for me in my perspective, that's something that also you need to think. Okay, and from this logic reasoning process, we may devise um, another process, like in industry, in a company, like many startups, uh, they have, we call agile organizations. You can also looking looking on your Google if you want to Google what does it mean agile organizations, which means every process inside uh, it should have uh, aside from logic, aside from how to solve problem, it need to have um, pace, okay, or speed, or pace. So you need to be uh, flexible, but in doing so, you need to also solve problem really well. And most of the startup or tech company nowadays, they tend to be agile organizations. And we can talk a lot about this, but I just want to show you um, what's the impact of math. So that I will going to show you some necessary uh, point for the report. Okay, so I assign uh, final report. Okay, this is due by January 16. Okay, so I hope you have time. Okay, now it's still 28 December. Not sure on what courses you will have for the final exam, but I hope for the final report it's still okay for January 16. Okay, the final report, hopefully this will be consist of at least, okay, minimum, at least having some intro, the main content, what you want to uh, discuss in your report, and also draw conclusions, or conclusions, and also I need your suggestion to our course, especially the method, the method of the courses. So if I want to explain here, if the introductions is, you need to also include why you think this is interesting, or anything you want to say here. Okay, you can also say and what it is. You can also state in the introductions. The main content can be about general idea, definition, and the process itself. Actually, the sections can be elaborate as much as you want. Okay, so it depends on you. Okay, so this is depend on you. Uh, the topic. Okay, the topic. You can choose the same topic as your presentation, or you can find your other topic. It's still okay for me, as long as you write from introduction to conclusions and have some suggestions about our course. Okay, suggestion about our course. So, for example, topic analysis or analysis about the usage of something, maybe formula or anything that you can find, and it's about the usage of blah blah formula on. You can write some specific other topics as well, maybe in physics or in um, maybe on structure, for example, in the buildings and on the building structures. So you can write down the intro, for example. Maybe you can start with uh, why this topic is important. Okay, and then you can state the background, like or your objectives here, what you want to show, and maybe at the main content, you can also add definition, visuals, some formula, and explanation on the topic itself. Okay, more explanation. So if you look at what I'm trying to say, it can consist of many things. Okay? Yeah, for the pages, I hope it is can be between 12 to 17 page. But if you think that you need to write more, I think maximum should be 20 something. Okay, so it can be 21, 23, or 25. Okay, I consider 30 is too long. Okay, so I think 28 is still okay. I think maximum 28. Okay, and for the it has to be related to engineering. No, it can be anything. It can be anything not related to engineering. Also okay. So if you think that your presentation topic is interesting, you can elaborate more. Maybe write in more details uh, what's your goal and what's your relations with maybe other topic as well. And then yeah, it can be anything. I think if you Google some articles, some website, I think there's a lot of things that you can input. Okay, like can mathematics, or maybe uh, what's the relations between mathematics and Maybe you can think any other topics that maybe it seems not related, but actually it can be applied to that fields as well. And maybe that will be interesting. You can also dive into those topics. Okay. Okay. Any other questions? So, how to get a good score in this final report? The more interesting topic you have. So first is this how to the scoring. Okay, how the score base. First is the topic itself. Interesting or not. So maybe you choose a topic that feels like a boring topic, but then in the introduction or in the main idea, you explain the topic and it getting more interesting. Okay, that is still okay. Still, it's really it's good actually. Okay, so the topic and also the structure. What the structure means is from the first sections until the conclusions, you have a good narrative. Okay, good structure, good explanations. The way you write is also has proportional reasoning. I think that also good. And your creativity. Your creativity. This is the main scoring for the final reports. Okay, just these three. So structure means that intro need to work align with the main content, and it need to work align with the conclusion. So actually, if you have objectives in the introductions, what's your goal in your report? You need to conclude in the conclusion. So this should be answers your question in objectives. That's actually what the conclusion means. Okay. And what kind of template layout, it's up to you. As long as it's easy to read, okay. Yeah. Oh yeah. Maybe one more thing. So creativity is also consists about design. Okay. So content and design. Okay, I think that's the idea. Okay. Any other question? This is probably around 40, around 40, 40 to 45, 40 to 45. So I think this will be really helpful. And we still have a final exam with written test that is probably around January, maybe after the report or maybe before. But I think I need to make sure that it's not too close with the calculus one. The calculus one is around, if not 13 to 14 or 12. Okay. Maybe this is around around 18, 11 or 18. So 11 January or 18 January. Okay, if I'm asking now, which one you prefer? January 11 or January 18? 18, right? After the report. Okay, after the report. So, or maybe any other idea for your final exam, the written test, 11 or 18. So I think 18, right? Because your report is deadline is January 16. You can still have at least sometimes to check and maybe to review, and then we will have a January 18. Okay. Okay. Uh, any other question? Okay. Any other question? Also, don't forget that tomorrow we will have the last presentation from Jordan, and also I need all of you to come and watch the presentations, because at the end of the presentation I will give you some forms to fill in. Okay. So yeah, I think that's it for today. So next week there will be no class. Okay, next week there will be no class, or if you want to have a class, still okay. But let's say the default now is no class. Okay, yeah, online, online, yeah. But if we have a class next week, I will let you know. Okay, probably I will just mention some topics that are not really discussed in the PBL presentation, and I think I will review some of that. Okay. So if there's no other questions, so we will end our course today. Hans, is it safe to use dominoes analogy for my topic? Uh, I think okay. Yeah, I think still okay. Still okay. And my suggestions for all of you for the topic, the more specified, I think it will be more. I think it will be better if you have like more specified, like not really in general. Like for example, today Helen talking about factors. Maybe you can specify what factors you are talking in, like maybe what's application or in what fields. I think that will be better. So your structure in your report will be more specifics. Okay. Okay. If there's no questions, then I think that's it for today. Okay. Let me stop the recording. Okay. See you tomorrow. Okay. See you tomorrow.